Okay, so now we come to the part 4 of the video for today's synchronous lecture, and I may consider this is the last part lah for chapter 5. Alright, okay, so we are going to discuss example 7. Actually, if you look at example 7 here, part of the solution we have solved in example 4. Okay, kalau tengok soalan tu example 4 dengan example 7 ni, the question is exactly the same. Okay, example 4 when we solve when we do the separation of variables. Okay, let's have a look at example 4 yang saya masukkan tu. Okay, here you are, example 4 where we have the question as this one, del u over del t equals to k del square u over del x square. U as 0 fx is the boundary the initial condition del u over del x 0 t is equals to 0, del u over del x l t equals to 0. And in fact here, okay, when we're done with the separation of variables, we're saying that it's to be continued in part 2. So we are going to carry forward the solution that we have so far here, where we have two differential equation same as sebelum ni yang kita discuss, and the most important thing is dia punya boundary conditions ni. Del v dv over dx at x equals to 0 is 0, dv over dx at x equals to l is also equals to 0. These two conditions make this example different from the previous example. Okay, now let's have a look. Okay, so sekarang ni kita ada apa dia tu, del v over del x. Okay, I'm not going to repeat. Dia punya method tu sama je dengan yang kita dah pernah, yang kita dah solve dalam example 5, right? Okay, so kat sini I have written that ada same jawapan yang sama yang kita akan guna for example 7, where we get all these answers we have worked out in example 5 before. Okay, jawapan yang sama, but basically we not example example 5, okay, where we do the separation of variables. Sebelum ni dalam example 4 part 1, and for this part we got the answer from example 5. Okay, what makes the difference is only its boundary condition, yang mana as you can see here, the boundary condition is del u over del x 0 t equals to 0 and del u over del x l t equals to 0. When we do the separation of variables, we have decide, okay, dia punya initial boundary condition dia adalah del u over del x at sorry, it's not u, it's v. Okay, del v over del x at x equals to 0 is 0, and then satu lagi initial condition dia, okay, another initial condition is del v over del x at x equals to l is also equal to 0, kan? Okay, so based on this, then we are going to check, okay, the three cases. Okay, kita dah ada jawapan untuk G. Okay, untuk GT, the solution for first order differential equation, this answer, this solution is still valid. Sekarang ni kita nak determine Vx, okay, where Vx is depend on our lambda condition. Remember how many cases we have for lambda? Kita ada 3 cases, right? V more than 0, lambda more than 0, lambda equals to 0, and lambda less than 0, by considering these two boundary condition. Del v dv over dx at x equals to 0, 0, dv over dx at x equals to l equals to 0. So now let's check each of the three conditions here for the lambda. Okay, so for lambda more than 0, dia punya possible solution dia still sama, which is okay, Vx is equals to C1 cos root of lambda x plus with C2 sin root of lambda x. Okay, what makes the difference adalah hanyalah dia punya apa? Dia punya boundary condition dia yang kita akan check sekarang ni, which is dv over dx at x equals to 0 is 0. Second one, dv over dx at x equals to L is equals to 0. So maknanya untuk check this boundary condition, extra step here, you kena differentiate V ni. So when we differentiate V, dV over dx, then you will get apa? Okay, cos differentiate, kita akan dapat negative square root lambda sin negative square root lambda C1 ni, ada lagi lah sin square root lambda x m plus with square root lambda C2 cos square root lambda x. Okay, so we substitute at x equals to 0, dv over dx at x equals to 0, then we have okay, negative lambda C1 sin 0, and then plus with square root lambda C2 cos 0. Okay, which is equals to 0. Dan daripada sini maknanya sin 0 ni kosong and cos 0 is equals to 0. So we left with square root lambda C2 equals to 0, and we know that okay, we know that lambda is more than 0. So between lambda and C2, definitely lambda ni tak boleh sama dengan kosong lah. So in this case, we come to the conclusion C2 equals to 0. So in this, bila kita tahu C2 equals to 0, maknanya sekarang ni dv over dx kita tinggal negative square root lambda C1 sin square root lambda x. Okay, yang ni dah jadi kosong. The second part turned out to be 0 sebab when we check for dv dx at x equals to 0, our C2 is equals to 0. Clear? Okay, so dv, we come to the second condition here, dv over dx at x equals to L is equals to negative square root lambda C1 sin square root lambda L is equals to 0. Okay, is equals to 0. Alright. Okay, so now, okay, so when it comes to here, kita akan ada this thing will equals to 0 when okay, lambda ni again cannot be equals to 0. So we have sin square root lambda L, which will make it equals to 0 kalau sin ni is equals to n pi. Sama je macam tadi kan. And then daripada sini kita tahu square root lambda L is equals to n pi. Then our lambda is equals to n pi over L square. Right. N pi over L square. So sama je lah macam solution tadi. Then we come to the conclusion that our Vx, okay, our Vx is equals to C1 cos, okay, square root of lambda tu kita ganti dengan n pi over L x. Okay, C1 cos n pi over L X. Okay, C1 ni nanti at the end dia akan hilang juga, ganti dengan BN macam tadilah. Okay, remember maksudnya this part gone sebab C2 we found out is equals to 0, and we using the first term lambda ni kita ganti dengan m pi over L square. So square root dengan square tu cancel each other, so that's why we come out with this for lambda more than 0. Okay, so now let's check for lambda equals to 0. Okay, for lambda equals to 0, dia punya solution is C1 plus C2X, kan? C1 plus C2X. So again, kita, Vx kita. Vx sama dengan C1 plus C2X. So we need to differentiate this time to check for its boundary condition. So dv over dx is equals to C2. Dan dari sini kita ada dia punya initial condition dv over dx at x equals to 0 is 0. So definitely daripada sini kita dapat C2 is equals to 0. Okay, C2 is equals to 0. So bila C2 equals to 0, okay, daripada sini straight away sebab dv over dx at x equals to L equals to 0 memang tak boleh nak pakai dah, sebab when you differentiate you just left with C2, kan? So we get C2 equals to 0. Daripada sini we straight away getting Vx is equals to C1. Okay, Vx equals to C1. Terus dapat, tak perlu lambda. So maknanya untuk lambda equals to 0, we get the solution Vx equals to C1. What about lambda less than 0? Okay, for lambda less than 0, kita punya Vx is equals to C1 cos square root of minus lambda x plus with C2 sin square root of minus lambda x, kan? Alright. Okay, so for lambda less than 0 ni, to check for its boundary condition, kita kena differentiate lah. So we need to find dv respect to dx, and the derivative for cos dengan sin ni tak silap saya masa dalam engineering maths 1 kita tak ada belajar, but dia ada formula dia, and don't worry, we'll put it in the list of formulas yang saya attach dekat Google Classroom tu, ya. So for your informations, cos differentiate we get sin, sama je sebenarnya, and sin we differentiate kita dapat cos. Dia tak ada positif negatif, semuanya positif. So differentiate C1 cos root of minus lambda x, kita akan dapat root of minus lambda C1 sin root of minus lambda x plus with minus root of minus lambda C2 cos minus root of minus lambda x. Okay, dan dari situ kita gantilah dv over dx at x equals to 0. Kita akan dapat minus lambda C1 sin 0 and then plus with root of minus lambda C2 cos minus root lambda 0 lah, maksudnya ini 0 equals to 0 kat sini. Dia sama juga macam sin dengan cos. Cos 0 is 1, okay, and sin 0 is 0. So turn out the first term everything becomes 0. So yang ni kita akan ada minus lambda C2 equals to 0. So from here we get C2 equals to 0. Okay, so bila C2 equals to 0, maksudnya for dv over dx at x equals to L, kita tak consider adalah the second term ni, kita hanya consider the first term. Sebab C2 kita dah tahu is equals to 0. So dari sini kita ada minus, okay, equals to minus root of minus lambda C1, okay, sinh minus lambda L equals to 0. Alright. So daripada sini we have two possibilities. Sama ada lambda ni sama dengan kosong ataupun C1 yang sama dengan kosong. But we know that the condition that we are talking now, sama je explanation dia sekarang. We know the condition that we are talking now is lambda less than 0. So in this case lambda tak boleh sama dengan kosong. So from here ternyatalah we need to say that lambda C1 equals to 0. So in this case sekarang ni, do we have a solution for Vx? We do not have solution for Vx because we have C2 equals to 0 and C1 juga sama dengan kosong. So maknanya the eigenvalues of lambda less than 0 is not the solution for our Vx. Alright, so our Vx solution is only for lambda more than 0 and lambda equals to 0. Okay, for the eigenvalue lambda equals to 0 and lambda more than 0. Okay, so now we come to the conclusion. For lambda more than 0, okay, just now we have solved kan, Vx is equals to C1 cos n pi x over L, okay, where our lambda is equals to n pi over L everything square kan. And if lambda equals to 0, okay, our Vs is equals to C1. Okay, kalau you all perasan kat sini, nampak tak? Okay, these two, okay, we have the same constant which is C1 and here is also C1. But the thing here is it is multiplied by 1. But tapi kat sini is cos n pi x over L. So from here, we may come to the conclusion that, okay, this is for n equals to 0. Maknanya kat sini masih lagi ada cos n pi x over L, but this is for n equals to 0. So when n equals to 0, it turn out to be 1. Faham? So that's why here this then we have Vx is equals to C1 only. Alright, and remember our GT last time kita ada, our GT is equals to C e to the power of minus k, okay, lambda t, right? But now we know that our lambda is equals to n pi over L square. So here we have C e to the power of minus k and n pi over L everything square t. So maknanya sekarang ni kalau kita nak darab uxt is equals to Vx times with gt, so we will have our Vx ni, we have two condition, right? Okay, kita take for lambda more than 0 and lambda equals to 0, and as I said before is for n equals to 0 and this one is for n equals to 1, 2, 3 and so on and so forth. Okay, so then kalau perasan here, okay, and here we have how many constants? C1, and we have a C here. So with this we regard all, okay, represent with a big constant. This time I consider this as a n. Okay, why a n? Because our function here, okay, is cos, not sine. So here is cos n pi x, okay, cos n pi x over L darab dengan e to the power of minus k n pi over L square t. Okay, and this n is starting from 0, 1, 2, 3 and so on and so forth. So when n equals to 0, cuba you ganti when n equals to 0, we will get the condition when lambda is equals to 0. Betul tak? When n equals to 0, kalau you cuba ganti when n equals to 0, we get a naught cos pi cos n 0. Ni yang ni maksud saya. Okay, when n equals to 0, then we get a naught darab dengan cos 0, then e to the power of 0, so is equals to a naught only. So this condition is true for lambda equals to 0 or n equals to 0. So makna kata this is actually our solution here is representing by apa? Okay, this part, if you look carefully, this is representing the Fourier cosine series, right? Fourier cosine series, okay? Where the final solution, you may conclude it as what have been written dalam soalan, dalam jawapan akhir kat sini. Okay, where the answer is equals to u at t equals to summation from n equals to 0 up to infinity a n cos n pi x over L e to the power of minus k n pi over L square t. Okay, bila kita apa nampak a n cos n pi x ni, because this one we may consider for all possible solutions. So we will sum up all the solution from n equals to 0 up to infinity, and following the Fourier cosine series, okay, to get the an, okay, to get the an coefficient, we use this formula. Okay, we use this formula, which is formula ni kita dah discuss before in chapter 4. So what is fx? Fx ni kalau dalam soalan biasanya dia akan berilah whatever function of fx, okay, maybe fx equals to x ke x square ke whatsoever, then you have to integrate in order to find the coefficient for an, just like example 6 that we have discussed before, where in example 6 we are using Fourier sine series, but here we have Fourier cosine series. Alright, so I hope I make yourself clear about this, walaupun maybe first time dengan discuss about this is a bit confusing. You try to redo it again on your own, then I'm sure you will get it more clear. Alright, then okay, before I end example 7, I want to clarify something here. What's the difference between just now we complete the solution, okay, we just found a n cos n pi x over L e to the power of minus k n pi over L square t, right? I'm saying that this is for n equals to 0, 1, 2, 3 and so on and so forth. Okay, actually I'm missing the subscript n here. Okay, maknanya solution ni hanyalah untuk one particular solution. If n equals to 0, macam tadi, when n equals to 0, then we have the answer is only a naught. When n equals to 1, maksudnya UXT kita is a1 cos pi x over L e to the power of minus k pi over L square t and so on and so forth. So the solution, the final answer here, it sum up all this solution, because u is equals to u naught e plus with u1 plus with u2 and so on and so forth. So that's why the the general solution will be the summation from n equals to 0 up to infinity a n cos n pi x over L e to the power of minus k, okay, times with the n pi over L square t. Okay, then to find n here, as I said just now, you are to find it using the Fourier cosine series formula, where you have to solve the integration depending on what is the function of fx. As of now, we just leave it because we do not know what is the function of fx. Okay class, this example 8 is actually your assignment questions. Your assignment questions. I will put up the assignment question at the Google classroom by end of maybe by this Thursday, or maybe right after I put up this video. So kalau you tengok, answer is already given, where this time the answer for this example 8, it involve a full Fourier series. We have A0, AN, and BN, in our solution, where we have a combination of Fourier cosine series and Fourier sine series. From where do we get this? Because we need to consider all the three cases of lambda, kan? Lambda more than 0, lambda equals to 0, lambda less than 0. So I want you to find out, from lambda equals to 0, what is our Vx? For lambda equals to 0, what is our Vx? And from lambda less than 0, what is our Vx? That will lead to this final answer. It's actually, if you follow example 7 and example 6 before, I'm sure you are able to solve for example 8 or your assignment question, to be particular lah. Alright, but before that, I will give you some hint to solve, because the question is still the same here. Sama je soalan dia ni, but what makes the difference is only these two boundary conditions. So I will give you a little bit of hint on how to solve this question for your assignment, which is, we have u, kan? We have u at t is equals to, we let it equals to v at gt, right? So maknanya yang ni, u negative lt here, it means that this is equals to v negative L times with GT, silap ni, GT ni. V negative L times with GT equals to VL GT. And then from here, we can make it, we bring everything to our left hand side, minus VL GT equals to 0. So in this case, we may factor out GT out. So we have V negative L minus with VL equals to 0. Equals to 0. Remember, when we want to determine the boundary condition here, we have two things to consider, where either GT equals to 0 ataupun yang ni, V negative L minus VL equals to 0. Refer back to the part 1 punya video last time. Video yang last week, asynchronous lecture. How do we determine the single variable boundary condition? So we have two options. Sama ada nak consider GT equals to 0 or the second part here equals to 0. But remember, we can't let GT equals to 0, because GT equals to 0 will lead to a trivial solution. So GT cannot be equals to 0. So in this case, we're going to choose the second one will be our boundary condition. So we have V negative L minus VL equals to 0. So in this case, we're going to have V negative L equals to VL as your boundary condition, the first boundary condition that you need to check in order to consider to check for each of the lambda case. Remember the steps on how we solve the partial differential equation, where you need to check for each lambda punya case in order to determine what is supposed to be your Vx, and that to check you need to rely on this boundary condition. Okay, then for the second one also, you may repeat the same step. It's just that the different here, this is the derivative, maknanya yang ni adalah d dx of negative L darab dengan gt equals to d dx of d dv lah ni, d dv of negative L, d dv of L darab dengan gt. Then you may proceed and you are able to get something like this as well. Alright, so try first to solve this example 8 ni, which is also the same question as in your assignment question. So I want everybody to work out for your assignment question only this question, and if I'm not mistaken there's one more question, but the first question is very simple. And for your information, this is once you are able to solve these questions, you are required to present also on how you solve these questions. Okay, on how you solve this question in a video presentation. Okay, the details about this, about the video presentation, I will put up a special guideline in Google Classroom, or I'll explain it in a WhatsApp or maybe in our Google Meet class very soon. Okay class, so that's all for chapter 5. Actually it will take quite a long time, this already half an hour for this part only. Okay, I know this chapter is quite tough, but don't worry, please try to digest it part by part, and inshallah at the end of the day you are able to understand how does the process go on. Alright, so with this we have completed chapter 5. Alright, anything you can reach me again. Okay, you can ask me, and we will have, okay, you can just text me, or maybe before the semester end we will have one Google Meet class in order to clarify through online session which part you do not understand in this chapter. Alright, so that's all for now. Then thank you. Assalamualaikum warahmatullahi wabarakatuh, and bye bye.